Okay, so on the last problem on part 5, okay, so this is kind of where this crosses over between electric fields and forces, okay? They're related, but it's kind of an Arkansas thing. Apologize if anybody's from Arkansas. So,
What do you mean by getting an Arkansas thing?
yeah, they're related, but kind of a different thing.
Oh, I see. It's not quite helping.
Yeah. So here's the deal. So here's what's different about the contrast on number 4 and number 5. So in number 4, you've got the 4 points and you're finding the electric field that's in the middle, okay? You're not finding the force on that particle. You're just finding the value of the electric field. So it's like a point in space, okay? There is no charged particle in that point in space. All you're finding is what the electric field is. Now, you can eventually find that force, okay? Because if you once you know the electric field, you can feck it. Because if you know the strength of your electric field and you know the charge that you actually put there, then you could actually calculate the value of the force on that charge. But an electric field in and of itself is just a value of that electric field in space, generated by a source that's generating that electric field. So here's what's going to be different on number 5. Okay, so this is why I wrote this part of it. So in number 5, you've got to build an equilateral triangle. What do you know about equilateral triangles? Here, who's the triangle king over here? Is that Eric? On your board who says there's, you know.
Yes.
Yeah. So Eric, what do you know about an equilateral triangle?
All the sides are equal.
So what is the angle between each side?
60 degrees.
60 degrees. So when you build this, the 2 bottom ones are easy to do because of the fact that it's just, you're here, okay? So the third one, if you really want to build this to get an idea what this is going to, there's a tape measure over here that you can drag over here. So you put these here in the middle, put this middle one at the 0.5, and then use that tape measure to get these at 1 meter. So here's the cool thing when you look at this in terms of the electric field. So it's emanating from here, so it's going towards this negative, and so basically you look at these field lines that are going in towards this one and out towards this one, and then they're circulating around and coming in like this. So what you want to find is the force that's acting on this top force up here. So if you think about it, this is where you need to start with the idea of which direction are these forces going to act. So don't even worry about this one over here. So you're talking about the net force acting on this particular one. So if you look at, you're going to have to use that F equals KQ1 Q2 over D squared. So don't worry about the magnitude for now. Which direction is the force going to act on this positive charged particle based upon that negatively charged particle down there? Which direction is it going to act? Towards that negative, or is it going to go away from that positive?
Towards the negative.
Yeah, so this force acting in this one is going to point in this direction, okay? So, and that's going to be at a 60-degree angle, so you can have a force coming down here like this. Calculate the magnitude of that using F equals KQ1 Q2 over D squared. You've got to change the nanocoulombs into coulombs, okay? And that's easy because the nanocoulombs is just 10 to the negative 9th. You have K, 1 times 10 to the 9th. It actually drops out 1 of your 10 to the negative 9ths, okay? And your distance is going to be 1 meter, okay? So that makes that simple. Then you've got this other force here. Now, with that one, what's going to happen? This force is going to tend to do what? Drive it away. So what you've got is that you've got one force vector that's going to push this thing down this way. You've got another force vector that's going to drag it, that's going to try and push it up this way. So this is where you've got to go old school, where you have to deconstruct the vectors. So when you have this, because the magnitudes are different, so you've got to take this vector and break it into its x and y components. Then you've got to take this vector and break it into its x and y components. Now look at this. What do you notice about the two x components?
They're equal.
No, not going to be equal because these charges aren't the same.
Oh.
But they're going to have the same sign anyway, right? So your x components are both going to be going in this direction. But you're going to have a y component in this direction and a y component in this direction, which aren't going to be the same because the charges aren't the same. So this is going to be a long slog in terms of the geometry. Take this vector individually, find its x and y components. When you do this, notice that I've given you a lot of room, okay? So say, okay, hey, here's this force. When I go to grade this, keep this thing organized so I can see what you're doing. So you're going to have this force, you're going to find its x and y components. You're going to have this force, find its x and y components. Now, in an ideal world, what I would have you do, if you really want to make this make it easy for an old physics teacher, you'd set up and go, okay, here's my x components, here's my y components. So this would be like force 3 and 1, and then negative 2 and 1. And so you would have these x components, these y components, and then you would have the sum. So that way, this makes it easier for me to see. So, oh, here's the x components of the first vector, here's the x component of the second one. Here's the y components here, okay? These x components, make them both negative, both positive, I don't care, okay? Because they're both going to be going in the same direction. Personally, I'd make them negative because it's like, if you look at where that's going, on an x and y system, it's over there in that second quadrant, so I'd make those negative. I'd make one of these positive, one of these negative, find the sum of these. So your actual magnitude of the force is that when you get done with this, you would draw a new triangle and say, oh, here's some of my x components, here's the sum of my y components. Now let me give you a hint. If you do this right, both your x and y components should be positive, which is going to push it over there into that second quadrant. So when you find the sum of your x components and the sum of your y components, both of them should be positive. So then you're going to come in here, oh, here's the sum of these x components. From the end of that, draw the sum of your y components, find that resultant, and find that angle. So since it's over there in that second quadrant, obviously your angle on number 5, part 4, has to be between 180 and 90. And it's going to be much closer to 180 than to 90. Okay? So, there you go. You're on your own. So, stop.